Welcome to this comprehensive guide on two fundamental concepts in C# programming, the singleton pattern and utility classes. Mastering these patterns is crucial for beginners, as understanding them will significantly enhance your software development skills, enabling you to write more organized, efficient, and maintainable code from the start of your journey. We'll start by exploring design patterns, which are essentially proven reusable solutions to common software design problems encountered in various contexts. These patterns provide a standardized blueprint for solving recurring issues, making your code not only more robust and maintainable, but also easier to understand and extend in the long run. Design patterns are crucial because they offer a common, shared vocabulary for developers, promoting much better communication and understanding within development teams. Furthermore, by applying these established patterns, you can create more flexible, scalable, and adaptable software architectures that can evolve with your project's needs over time. Chapter 1. The Singleton Pattern. The Singleton pattern ensures that a class has only one instance throughout the entire application's lifecycle and provides a global, well-known point of access to that unique instance. You can think of it like a single, central control panel or a master switch for a specific system, where all operations must go through this one designated entity. The primary purpose of the singleton pattern is to strictly control access to a shared resource, preventing the creation of multiple instances that could potentially conflict with each other or consume excessive system resources. This controlled access is vital for efficiently managing unique system components, ensuring consistency, and preventing data corruption. Common and practical use cases for the singleton pattern include logging services, where all log messages are routed through a single logger instance, configuration managers that load settings once, and database connection pools, where only one instance should manage and distribute connections to optimize performance and resource usage across the application. Chapter 2. Implementing a thread-safe singleton. Implementing a thread-safe singleton is absolutely crucial to prevent potential issues like race conditions and inconsistent states in multi-threaded environments, where multiple threads might try to create the instance simultaneously. We'll explore two common and effective approaches for achieving thread safety, using the lock statement and leveraging the lazy T class. The lock statement in C# ensures that only one thread can enter a critical section of code at any given time, effectively creating a mutual exclusion zone. This mechanism is vital for preventing race conditions, which occur when multiple threads attempt to create the singleton instance concurrently, leading to unpredictable behavior or even multiple instances. While the lock approach is effective for ensuring thread safety, it can introduce a noticeable performance overhead, especially due to the constant locking and unlocking operations. Although it's a straightforward and easy-to-understand method, it might not be the most performant or scalable solution for applications experiencing high-contention scenarios where many threads frequently compete for the same resource. A more modern, elegant, and highly efficient approach for implementing thread-safe singletons in C# is by utilizing the lazy T class. This class provides built-in lazy initialization, meaning the singleton instance is created only when it's first accessed, not at application startup, and it handles all the complex thread safety mechanisms automatically and efficiently behind the scenes. Here's a practical C# code example demonstrating a robust and thread-safe singleton implementation using the lazy T class. Observe how remarkably concise and readable the code becomes, as lazy T effectively abstracts away all the complex, low-level synchronization logic that you would otherwise have to manage manually, making your code cleaner and less error-prone. The significant pros of singletons include providing strictly controlled access to a sole instance, which is excellent for efficient resource management and ensuring global consistency. However, a major con is that they can easily become an anti-pattern if overused, leading to tightly coupled code that is difficult to modify and maintain, as components become overly dependent on the global singleton instance. Singletons can also significantly complicate unit testing because their inherent global state introduces hidden dependencies across different parts of your application, making it challenging to isolate components for testing. This global state can lead to test order dependencies and make it harder to mock or substitute the singleton, so always carefully consider these crucial trade-offs before implementation. Chapter 3. exploring utility classes. Now, let's shift our focus to utility classes, a different but equally important concept in C# programming. These are specialized classes that contain only static methods and, crucially, no instance-specific state. They are essentially straightforward collections of helper functions designed to perform common operations without needing an object instance. Utility classes are incredibly useful for encapsulating common, reusable functionalities that inherently do not require or modify an object state. They provide immense convenience by offering readily available methods and significantly promote code reusability across various parts of your application, reducing duplication and improving consistency. Excellent examples of utility classes include the built-in system, math class for performing various mathematical operations, or custom classes you might create for common tasks like string manipulation, file operations, or data validation. The key characteristic is that these methods perform their actions purely based on their input parameters, without affecting any object's internal data or state. Chapter 4. Creating custom utility classes. Creating a custom utility class in C# is quite straightforward. You simply define a static class, which means all its members must also be static, and fill it with your static methods. As a best practice, these classes should also be sealed and have a private constructor to explicitly prevent any accidental instantiation, reinforcing their stateless nature. Here's a simple yet illustrative C# code example of a custom utility class designed for basic string operations, perhaps named string utils. Notice how all the methods within this class are declared as static and operate solely on their input parameters, returning a result without relying on or modifying any internal state of the class itself. A key and absolutely critical best practice for utility classes is to rigorously ensure they remain stateless. This means they should not hold any data that changes over time or between method calls, as introducing state can lead to unexpected side effects, make the class harder to reason about, and complicate its management and testing significantly. It's also important to consider the subtle but significant distinction between utility classes and extension methods. While both serve to provide helper functions, extension methods offer a more object-oriented approach, allowing you to add new methods to existing types without actually modifying their original source code, making them feel like native members of the type. Chapter 5. Singleton versus utility classes. Let's now directly compare singletons and utility classes to highlight their fundamental differences. Singletons are designed to manage a single, stateful instance throughout the application, providing a global point of access to it. This is typically used for managing shared resources, application-wide configuration settings, or services that require a consistent state. Utility classes, on the other hand, are fundamentally different. They are stateless collections of static methods, meaning they do not maintain any internal state across calls. They are specifically designed for common, reusable operations that perform calculations or transformations purely based on their input parameters, without needing an object state or affecting external data. You should choose a singleton when your design explicitly requires ensuring that only one instance of a particular class exists throughout the entire application, and you need to manage its state globally. Ideal scenarios include a single logging service, a centralized configuration manager, or a unique factory that coordinates object creation. Conversely, opt for a utility class when you have a cohesive set of related, stateless functions that perform operations purely on input data, without needing to store or modify any internal state. This is perfect for tasks like mathematical calculations, string formatting, data conversions, or any general-purpose helper functions that don't belong to a specific object instance. Chapter 6. Best Practices and Tips. For singletons, a critical best practice is to avoid overuse. While they are powerful for specific scenarios, they can easily introduce global state into your application, making it significantly harder to test, debug, and maintain. Use them judiciously and only for truly unique, application-wide resources where a single instance is a strict requirement, not just a convenience. Always ensure your singleton implementations are robustly thread-safe, especially when operating in concurrent or multi-threaded environments. Failing to do so can lead to severe issues like data corruption, inconsistent states, or unexpected application behavior. as multiple threads might interfere with the singleton's creation or access simultaneously. The lazy Teague approach is highly recommended for this. For utility classes, the most important principle is to strictly adhere to statelessness. This means no instance fields or properties that hold data. If you find that a method needs to maintain or modify state across calls, or if it depends on an object's internal data, it's a strong indicator that it likely belongs in an instance class, not a utility class. Furthermore, keep utility classes highly focused on a single, well-defined responsibility. For example, a string utils class should exclusively handle string operations like formatting, parsing, or validation. It should not contain methods for file I/O, database access, or network communication, as this violates the single responsibility principle and makes the class less reusable and harder to manage. Chapter 7. Conclusion. In summary, we've learned that the singleton pattern provides a single, globally accessible instance primarily for managing stateful resources or services that require unique control. In contrast, utility classes offer stateless, reusable helper functions that perform operations without needing an object state, serving as convenient toolboxes for common tasks. Both the singleton pattern and utility classes are powerful and valuable tools in C# development. However, their effective and appropriate use critically depends on a clear understanding of their distinct purposes, their underlying principles, and diligently adhering to the best practices we've discussed to avoid common pitfalls and maximize their benefits. By applying these patterns wisely and thoughtfully, you can write significantly cleaner, more efficient, and ultimately more maintainable C# code that stands the test of time. We encourage you to keep practicing, experimenting, and exploring their diverse applications in your own projects to solidify your understanding and become a more proficient developer.